Tammy Rosanio here in the room directs our partner program. If your firm or institution is not currently part of our partner program, I encourage you to talk to Tammy and learn the benefits. Got an elite group here in the room at SyracuseCoE today, and also a great group that's listening into this forum online, and I welcome you both. It's my pleasure to introduce the person that will introduce the speaker. You saw in the announcement our moderator for this program is Hugh Henderson, and you saw a two-sentence overview of Hugh's background. I want to embellish that just a little bit. I've known Hugh for, I think, 20 years, plus or minus 2 years. In fact, I don't know, I have to ask Hugh. There was a meeting I often talk about in 1998 at O'Brien and Gear where the idea for the Center of Excellence was conceived. Oh, Hugh wasn't there. Okay. But I'm surely met Hugh shortly after that, so Hugh is a native of upstate New York. He was born in Oneonta. He went to Cornell, got both a bachelor's degree and a master's degree in agricultural engineering. After graduation, he worked for Carrier here in Syracuse. And then he went to Florida and he worked at the Florida Solar Energy Center. And then he was attracted back to his roots, back to Syracuse. He worked for a firm called the Fleming Group. And then 22 years ago, with two partners, he founded a company that was called CDH Energy. So Hugh's the H, together with C and D. Over the years, C and D left, and Hugh was the owner and operator of CDH Energy. 4 years ago, CDH was acquired by the Gas Technology Institute, a nonprofit organization in Illinois. And that GTI actually acquired a few other firms, and in January has rebranded its capabilities across these 6 firms as Frontier Energy. So Hugh is now Vice President in the Building Research and Energy Consulting practice at Frontier Energy. Frontier Energy has 6 offices and 130 people in California, New York, and Texas. Hugh leads field monitoring and energy analysis projects, evaluating a range of HVAC, combined heat and power, and building energy efficiency projects. Hugh has collaborated with SyracuseCoE and with me personally on, I'd say, dozens of projects of varying scales over the last 15 years. Including houses that we built and monitored in the near west side, and domestic hot water heaters, which we ran here in a lab at SyracuseCoE and also in the field and field houses. Hugh's helped redesign houses that are now being constructed by Home Headquarters. Worked with Jensen Zhang in a laboratory here to study unintended airflows in a project that included this Solar Energy Center, Florida Solar Energy Center collaborator. So it's been one of the best industry collaborators for applied research projects with SyracuseCoE all over the years. And it's really my pleasure to recognize and thank Hugh for his service on many projects, and in particular on the project that we're going to hear about today. Hugh helped Ryan in conceiving the experimental apparatus that Ryan's going to talk about. So now, without further ado, here's Hugh Henderson.
Yeah, hello. This is a great topic, and I have been involved in this project a little bit, figuring out how to test this. And I've gotten to know Ryan a little bit. So I'd like to introduce Ryan Milcarek. He's obtained all his degrees from Syracuse University in mechanical and aerospace engineering, and he's actually about to change climates and go to the School of Engineering, Matter, and Energy Transport at Arizona State University, and that makes sense after spending a long time in Syracuse. It'd be good to try something else. So that makes total sense. Congratulations on that appointment. And he's been working on this concept of a flame-assisted fuel cell, I think, for several years, a good portion of his time here. And I think going back to your undergraduate work, I think you had started on this. And he's had several distinctions. I think he's an NSF Graduate Research Fellow, JSPS International Research Fellow, and an ASHRAE Grant and Aid recipient. And he's also a recipient of ASME International Gas Turbine Institute scholarships and other things. And it's my pleasure to introduce Ryan.
Let's just invite, if people were watching the webinar and have questions, they should type it into the chat box, and I'll come into the room, carry over later.
Okay, that's perfect. Yeah, so I think we'll probably say big picture questions maybe for the end, but if we're in the middle of something and you really get lost, you feel free to jump in, and I don't mind going a little bit slow so we can make sure we cover this. I'll try and stay next to the mic. I like to walk around, but I'll try not to do that today. So yeah, I'm about to switch positions. So this is the bulk of my research that I've done here at Syracuse, but I'll continue on this in some slightly different directions, and we'll talk a little bit about that at the end at Arizona State University. As we get started here, I'd just like to acknowledge the support of really a lot of organizations that have made this happen. It started off with DOE funding and really worked its way down. So this is busy. I'm not going to have you read the whole thing. Let me just kind of break it down for you. So I started back in 2014 on my PhD, and actually in the lab here with Dr. Ahn a little bit before that, so during my undergrad. And we applied for funding through the MTech program, and we received that funding. That was really just the really preliminary data that made this happen. I'm going to show that at the very beginning, and it was fairly successful. And so we moved on, and we said, well, let's try and build a kind of a bench scale system of this, and that happened under a NYSERDA contract. We then, I received some funding from the NSF under a fellowship, which was great to support myself. But ultimately, as we continued to move forward, we found funding from Nexus New York that helped us take it from a bench scale system to really a full scale prototype. And we might even have a chance to see some pictures of it at least. And it's actually here in the Center of Excellence, so you can check that out. And then as all this was happening, we kind of started to see, I started to see some of the limitations of the technology. And so we started to explore some of those through what's called a JSPS fellowship. That's the Japanese Society for the Promotion of Science. It's their version of the NSF, basically. And we collaborated with the Tohoku University, who does some great work in microcombustion. So I'm only going to touch on that just a little bit. That's not my main focus today, but I'll get into that just a touch. I'd also like to acknowledge the support of really a lot of faculty who have been involved in this project, from my advisor, Dr. Ahn, to Dr. Wang, who was just finishing up his PhD as I came in. We had a very short time together, but I'll talk a little bit about that project towards the beginning here. And then all the way to our collaboration in Japan with Koro Maruta and Hasashi Nakamura, who are doing great work in microcombustion at Tohoku University. And of course, those are the faculty, but the students really drive a lot of the work, right? And so I've had great students I've been able to work with over the years, from Michael Garrett, who's an intern here at the COE, to Tom Wells and Vinny DiBiase, who just both actually are recently started in our lab. So grateful for all their support. So let me give you a quick overview. I'm going to try and motivate this, and we're going to take a few minutes to motivate it, just to really try and understand what are we talking about when we talk about extreme weather, why do we need resilience, and how is heating connected to all of this. I'm then going to kind of take a deep dive into the technical aspects, and hopefully you stay with me on that. I'm going to try and explain fuel cells really hopefully simply, and then go into some of the initial developments all the way up to that Nexus grant where we kind of made a full-scale development, and that's where I'll start to talk about some of the applications of the technology. And then we'll just delve into microcombustion just a little bit, all right? So I always like to show this picture first. You all know where we are. We're here at Syracuse, and I always joke, this is the pictures that they show you when you apply as a student, right? It's on all the application brochures, and as soon as you get here, they show you the truth, right? We start to warn students about what's coming, right? And we're kind of used to this. This is our environment. We live in this, I mean, for at least 6 months a year, right? There's snowing. Well, maybe a little bit less. I got to drive. I got to motivate my point, right? And so we have snow, Why are we concerned about it? We're concerned because these extreme weather events seem to be trending, and it's not just the extreme weather that we're concerned about, it's what happens as a result. So on the axis here, you see number of outages, all right, number of power outages, and then you see how much they're increasing over time. Unfortunately, I couldn't find newer data than 2012, but you kind of see the general trend. We seem to be seeing more power outages, and they seem to be linked to extreme weather. That's the general trend. One example that you're probably all very familiar with is Sandy. Sandy came through, more than 8 million people lost power, right? And as you can see, I think that's actually really amazing about this, looking at it a different way here, is really they did a pretty good job of decreasing the bulk of it, 75% within the first 4 or 5 days. But if you're this person right here, or these couple hundred people, it doesn't matter, right? You've lost power, and by then the damage is done, unfortunately. This is one example. Sandy happened, and it took a couple weeks really to get power restored, and obviously much, much longer to really restore normal life. Let's look at what does that mean for your house? If you lose power, well, within a couple of days, the temperature in your house starts to go down. Now, even if you heat your house with natural gas or propane or some sort of fuel oil, within a few days, the temperature in your house will be below freezing. This is a study that was done by the Department of Energy. They looked at different housing types, and of course, it's very dependent upon that. But generally speaking, within 3 to 7 days, you start to see a lot of the houses start to approach the point where the temperatures are freezing. If the temperatures are freezing, your pipes are going to freeze, and there's going to be damage associated with that. Now, we might think, well, this is just a northern climate issue, right? But unfortunately, it happens everywhere. You might remember this, the bomb cyclone just this year, right? Actually, a couple of them. I wasn't so familiar with bomb cyclones until this year. But this is an example here. We look at Virginia Beach in Georgia, 8.5 days straight with below freezing temperatures. These are not locations where you typically see freezing temperatures, but these things are happening when we look at extreme weather. And so if these extreme weather events continue to trend, and if we don't have a resilient way of heating our homes, the power goes out, we're going to have potentially a lot of damage to clean up in our homes and in our communities. So why does this happen? Well, if you look at the big picture, that's kind of what we're going to try and do on this slide. We want to look at the big picture. Typical furnace, about 100,000 BTUs per hour. That's about 29 kilowatts. And that's the chemical energy, essentially, that's coming in. We're converting it to thermal energy, and that's what's heating your house. Okay. Now, within that furnace, there's this not so small piece, but it really is, if you look at it in terms of percentage of power, there's this piece called a blower. That's what's actually pushing the air to your house, right? And then the thermal energy to your house. That blower consumes about 1 to 3% of that total chemical energy, but it doesn't come from the chemical energy. We supply it with a separate feed by electricity. So you have fuel coming into your house, and then you have electricity coming into your house just to run the furnace. But as you can see, the amount of electricity you need is quite small compared to the amount of chemical energy that's available. So what if we rethought this entire picture? Instead of converting all of this chemical energy to thermal energy, what if we converted just a little bit to electrical energy? So say, for example, 98% of the chemical energy becomes thermal energy. We convert the other little 2 or 3% to electrical energy. One way we can do that is using a very conventional furnace, which we all have, or a boiler if you have that. Those are in many homes. And combining that with a solid oxide fuel cell to convert some of that chemical energy to electricity, now we have a system that can do thermal energy and electricity. Very, very different. And now we have this idea of a resilient furnace. You no longer need to worry about the power going out. Your furnace can still heat your house because it provides its own electricity through the fuel cell. Okay, so we're not breaking the laws of thermodynamics. We're going to use the fuel cell to convert some of the energy. That's kind of the premise that this whole project started under, and this is essentially what I was given when I started my PhD. There'd been some work done, but this is kind of the big picture of it. So looking at a solid oxide fuel cell, this is where we start to kind of talk about the technical side of it. How does this work? A solid oxide fuel cell is all ceramic. Okay, this electrolyte layer is typically a very dense ceramic material, such as a uretria stabilized zirconia. And it's surrounded by 2 electrodes, a cathode and an anode. On the cathode side, we typically supply air. You can supply, complete 100% oxygen, but it's obviously much more expensive to do that. So we usually try and supply air. The air comes in. The oxygen will actually diffuse through just regular diffusion through this porous cathode layer. It comes to this what's called triple phase boundary, where the electrode meets the electrolyte. And electrons coming over from the anode side go through an oxygen reduction reaction to create oxygen ions, which are here. At high temperatures, there's oxygen vacancies within that electrolyte. And so those oxygen ions are actually able to jump from vacancy to vacancy through the electrolyte. They come over here to this side of this other triple phase boundary where the anode electrolyte boundary is, and they can combine with fuel through this half reaction. So for example, hydrogen and an oxygen ion can form water and the two electrons that are needed to complete the circuit. And then the electrons are ultimately going through the external circuit here. And here's that half reaction for oxygen. So hydrogen's one example. It's the most common one when you think of fuel cells, we think of hydrogen. But of course, we can also use carbon monoxide. You can think of a very similar reaction that forms carbon dioxide. The only challenge with carbon monoxide, though, is that occasionally at certain temperatures, this what's called inverse boudoir reaction actually becomes very favorable. And if that's the case, we can actually deposit carbon within the anode, and after a period of time, that anode can be completely covered in carbon, and they're no longer able to transport the fuel through it. So the fuel cell will no longer work. Carbon we have to deal with, but it's possible if we can control the temperature properly. We can also even think of a reaction for methane. In this case, you can think of methane reacting directly, but as you kind of look at this picture, you can say one methane molecule and 3 oxygen ions all meeting in the same place at the same time, allowing this reaction to happen perfectly. Doesn't really happen like that from a kinetic standpoint. Generally, what we find is that methane will often actually go through a similar carbon deposition process. The carbon will then be oxidized and then further oxidized to carbon dioxide. It's kind of a step-by-step process to that. So generally speaking, solid oxide fuel cells can operate with hydrogen, carbon monoxide, and methane. Those are the 3 main fuels. We'd like to use bigger hydrocarbons, right? It'd be nice if we could just use gasoline directly, but carbon deposition becomes very challenging. So that's the fuel cell. And you look at this slide and you say, this is kind of complicated, but that's kind of the point. Here's the fuel cell, and here's everything else that you need to actually make this happen. The system's fairly complicated, actually. What you need to do is we need to take air and fuel. We typically desulfurize the fuel because sulfur also has some issues with the anode materials, similar to the carbon deposition problem. We then supply water, bring it up to temperature so that it forms steam, and then we use that steam in what's called a steam reformer for these steam reforming reactions. And so even though we can use methane and carbon monoxide, we generally find that hydrogen has much faster kinetics. We can also use butane in a very similar reaction, or propane, much higher hydrocarbons. And going through this steam reforming reaction, we can actually form syngas. We can then utilize that hydrogen directly and supply that to the fuel cell. So this is typical. Steam reforming is very common in solid oxide fuel cell systems. We then will combust, and usually any remaining fuel that's left over, supplying that heat for all the heat exchangers. As you can see, there's 4 levels of heat exchangers here. And then this is what actually would bring the heat to your house if this was in your house. And then this is the power electronics associated with getting the DC power to AC, or depending on what your needs are, you need some sort of power electronics and power conversion. So that's a general picture of how this system works. What are the challenges? Well, they operate at 500 to 1,000 degrees Celsius, okay? And when they operate at that temperature, because this is a ceramic material and it needs to be sealed very well, we typically start up at a rate of about 5 degrees Celsius per minute. Okay, so 5 degrees Celsius per minute up to 500 degrees. You can do the math really quick, right? That takes a long time. This isn't a car. You don't just hop in and you turn your system on and it just goes. It takes a while for these things to heat up. So I want you to remember that 5 C per minute because that becomes very relevant later. Also, right now, the DOE and a number of organizations, they're really trying to push the limit of these solid oxide fuel cell systems to cycle, to basically turn on, turn off, turn on and off again. Very challenging, actually, because, again, they're sealed so well that if we turn them on rapidly, and if we do it many, many times, those seals start to break. And so some of the challenges here, they're really trying to push 100 cycles. That's the goal. And of course, at high temperatures, these materials start to degrade, and we have a lot of compatibility issues with different materials going from ambient temperature all the way up to 1,000 degrees Celsius. So this is kind of big picture solid oxide fuel cells to give you a brief introduction. So where did we kind of start? Well, in 2004, they started to look at a different concept, and this is from Horiuchi's group actually in Japan. They kind of came out with this. Everyone was talking about the dual chamber. We take the fuel cell, we have a specific fuel chamber, we have a specific oxidant chamber, we seal it really well, and we don't allow the two to interact. Well, they kind of changed that idea. They said, what if we just kind of got rid of the idea of chambers and we just put the fuel cell right in a flame? The flame acts as a reformer. It can take high hydrocarbons like gasoline and reform them to syngas. It also provides the thermal energy to bring the fuel cell up to temperature. And now that the fuel cell is no longer sealed in place, you could actually heat these things fairly rapidly and potentially cycle them a little bit more, okay? And so that was the idea. It's simple, this direct flame fuel cell idea. It's simple, we have no chamber, fairly fuel flexible, and there's possibilities here with trying to start up and shut down rapidly. So that's what happened about 2004, and about 20 or so papers were published, and this is the things that we started to learn about these direct flame fuel cells from that initial research. So again, here's our fuel cell, here's the electrolyte, the anode, and the cathode, top view. Here's the flame burner. You can use a lot of different burners here, right? And actually a lot of work was done just looking at what kind of burner would optimize this kind of system. Turns out that within the flame, you can find significant amounts of hydrogen, right? And some carbon monoxide. CO2 doesn't hurt the fuel cell, but it doesn't help either. It just kind of dilutes the fuel. So ultimately, if we're in certain locations, we can find quite a bit of hydrogen that we might be able to convert to power with the fuel cell. But if we're in other locations within the flame, that composition changes significantly. In fact, as you get closer to these edges, you can see it yourself. There's air everywhere, right? This is an open flame. And so as the air diffuses in, we're going to have this syngas that we're intentionally trying to generate with the flame is going to be reactive. And so now we have much less hydrogen, much less CO. We have a lot of products of combustion. We ultimately have no power. As you can probably guess, depends really at where you are in the location of the burner. Initially, everything coming out of the burner is the fuel and the oxidant itself. As it starts to go through these reactions, it proceeds down the line. Ultimately, the fuel breaks down into hydrogen, then forms into water and carbon dioxide. It's kind of a process that happens there. And it turns out that based on where you are compared to the burner makes a big difference for the fuel cell. So 0 here means we're basically going to take this fuel cell anode, we're going to put it right at the burner. And it turns out if you're right next to the burner, the temperature is very low because the reactions are just starting. You haven't released a lot of the thermal energy yet. And it also turns out that because it's low and you mostly have methane still left over if you're using methane directly, your voltage is actually very low. You can see it actually becomes 0.1 volts. That's not a useful fuel cell. If we're very far from the fuel or from the burner, now we're basically operating clearly in the exhaust and there's not much fuel left there, right? Because it's going to be oxidized. And so again, the temperature becomes low and again, the OCV is low because there's not much fuel left over. And so it turns out in this direct flame fuel cell, this was really some of the early work that we did, we kind of realized there's really a sweet spot. You got to have the fuel cell right in the right location in order to have high temperature and high voltage in order to get fairly high power density and efficiency. Well, what does that mean? It means that you can only have so much fuel cell area that you can actually get within that physical location. And fuel cells are kind of a unique power conversion device. They really go by the area. The larger the area, the more power you can generate. And so if we're limited by the area that we can actually get into that optimal region, there's some real challenges. And of course, that led to basically 10 or so years of research, and the ultimate conclusions were we can only utilize about less than 1% of the syngas that's actually available. You see that figure pretty commonly in literature. So we're only utilizing less than 1% of the fuel. What does that mean for the efficiency? Well, it has to be less than 1%, right? And it generally, over the years, this pretty much summarizes the last 10 to 15 years of research on these direct flame fuel cells for an average efficiency of less than 0.2%. And that's not 20%, that's 0.2%, okay? So it's really major challenge. There's a real opportunity here. It's very simple. It can start up rapidly, but the big picture is the efficiency is not where it needs to be, and we're struggling to have the fuel utilization that's necessary. So that's kind of where this all started. We did a little bit of work in this area, and we started to rethink how we were going to approach this. So we made one small change, very, very small, and maybe it's not obvious, but hopefully it will be after I explain this a little bit more. So this is the initial setup. This is the direct flame fuel cell. You've got your fuel cell here. We're operating near the flame. We're allowing excess air to diffuse in, and ultimately that's part of the problem. It's kind of combusting whatever fuel we're actually trying to generate. It's ultimately will if we're far away from the flame. So instead, we decided, what if we prevent this excess air by enclosing this system. So essentially we go from a no chamber back to a dual chamber of sorts, a little bit different kind of dual chamber setup. But we're going to try and use the flame for the same things. We're going to try and use it for rapid startup, and we're going to try and use it for reforming of the fuel. That's kind of the goal. And ultimately, what we're doing in combustion-wise is we're switching from what's called a partially premixed flame. It is premixed here, but it's kind of partially premixed if you're adding extra oxidant, to a completely premixed flame. That's what we're switching. One small change. Let's see what happens in the exhaust. Now we no longer have to be near the flame, right? We're not allowing the syngas to oxidize. We can be kind of anywhere. We can be far downstream of the flame, actually. And so the first thing we needed to do was, and this is what we did with that Amtech project, is we developed a combustion chamber. We took our fuel. In this case, we were studying methane because methane is a pretty good model for natural gas. Most of natural gas is methane. We mixed it with air, and then we supplied it here with a burner. This burner is basically the same dimensions of a typical in-shop burner that you have to heat your house. And then we have the combustion process happening here. We're monitoring the temperature, and then ultimately we're going to pull exhaust from it. We're going to send that exhaust to the gas chromatograph, which is going to analyze the composition of the exhaust, and we're going to measure the temperature, okay, with K-type thermocouples. We did that, and this isn't a very new experiment. In fact, a lot of combustion scientists already understand this pretty well, but we're building off of this as our initial starting point. And what we found, of course, 1 means stoichiometric reaction. So at an equivalence ratio of 1, we have basically enough oxygen to oxidize all of the fuel. So all your fuel should be utilized at this point. And as we see high carbon dioxide, oxygen is essentially, in this case, there's a little bit of oxygen left over. That's a kinetics issue, but usually it's close to 1% at equivalence ratio 1, and very little fuel remaining. But as we increase the equivalence ratio, meaning we now have extra fuel and not enough oxygen available to completely oxidize it, now we start to see significant carbon monoxide and hydrogen being generated at higher equivalence ratios. So even at an equivalence ratio of 1.4, we saw about 12% of the exhaust was hydrogen and about 8% was carbon monoxide. Now you might ask yourself, why did you stop at 1.4, right? Just keep going. Well, the challenge with combustion is typically we want to operate near stoichiometry because that's where the reactions can happen very readily. But if you become very fuel rich, the reactions can't actually sustain themselves. There's not enough heat release from the flame to keep the reactions going, and so the flame ultimately will extinguish as you get extremely rich. And so in our case, in an equivalence ratio of about 1.4, just beyond that, the flame extinguishes. That's kind of the end of the story for this kind of technology at this point. So with that, we wanted to make one other change. We're switching from a partially premixed system to a completely premixed system, and we're also going to switch from a planar solid oxide fuel cell to what's called a microtubular fuel cell. These are the tubes, and I've actually got one example there which you can pass around if you want it. They're very small, and you'll see some pictures of them. Yeah, that little bag right there. So they're a tubular geometry, and this is kind of a profile view, so you can kind of get a sense of what these look like when they're all stacked together. Why did we switch to these tubes? Because they're a lot easier to seal. Remember I said the sealing was part of the issue with the dual chamber. Well, these are a little bit easier to seal, and we found over time with a lot of research that you can generally heat these things up a lot faster, and we can also thermal cycle them. Up to 400 cycles at least has been done, and 361 degrees Celsius per minute is a whole lot better than 5C per minute, right? So these are the microtubular solid oxide fuel cells. We started developing those. To develop them, we go through an extrusion process. You probably maybe had an extruder if you played with Play-Doh before, right? You push the Play-Doh through and it goes through this die. It ultimately forms this tube shape, which is here. This gives you a sense of what it looks like. Here's a dime for comparison. We then take the tube and we dip it in this slurry. It's a liquid that's very viscous, essentially. And this is our electrolyte material with some other additives. We then dry it, and ultimately we'll sinter it up to 1400 degrees Celsius where that electrolyte material will densify properly. We then take that electrolyte, or the fuel cell with the electrolyte on, we then dip it in a cathode material and ultimately allow that to dry and then sinter it to 1100 degrees Celsius. We can get into, if you're curious about the temperatures, we can talk a little bit more about that, but different materials need different sintering temperatures. And then ultimately, once we've got the cathode on, we apply what's called current collector. We need to get the electrons on and off the fuel cell, right? And so for the cathode, we're using some silver paste here and silver wire. And you can't actually see it, but we have, this gold is on the anode and it's directly connected to the anode. We don't have electrolyte all the way. And you can kind of get a sense of the size. And if you look at the little sample that's going around, these are fairly small, right? About 2.4 millimeter internal diameter, microtubular solid oxide fuel cells. So what does all this mean? It means now we can take our fuel, we can pre-mix it in a chamber, we go through a combustion process, we then send that exhaust directly through a microtubular solid oxide fuel cell, and then if there's anything left over, we can allow for complete combustion in the downstream, okay? So we've already looked at this area, what happens between the fuel and the exhaust and the fuel-rich combustion process. The next question is, what happens when we put this really diluted fuel, right? This is kind of dirty fuel. We have very little hydrogen and carbon monoxide, but we have some. And we take that with our other products of combustion and we send it directly to a fuel cell. How does a fuel cell perform? So in order to do this, we could have built the entire system ourselves, but we're working on a very simple setup here and just kind of trying to get some initial results. So we pre-mixed the major gas species within the exhaust. We didn't use water. Water has some complications, and it's actually difficult to measure with a gas chromatograph. So this is ignoring water. This is basically the dry exhaust, but most of the composition of the exhaust is here. We then take this exhaust and we ultimately determine flow rates associated with it. So of course, at higher equivalence ratios, we have higher hydrogen, higher carbon monoxide that we're supplying, and in return, we have less carbon dioxide and less nitrogen that's being supplied. What does that mean for fuel utilization? Well, we didn't optimize it completely, but we wanted to understand the fuel utilization to some extent. Remember I said less than 1%. That's kind of the magic number for fuel utilization in direct flame fuel cells. Well, this kind of shows that it's actually possible to push well beyond that. We saw up to about 33% fuel utilization was possible. And again, this is happening within a controlled environment. We have a furnace, so this isn't that we're actually heating our fuel cell in. So this isn't perfect. We're also controlling the flow rate, but there's no chemistry limit here where we can't get beyond 1% fuel utilization. If we could, the project might have ended here and we would have been done. But we can see that it is possible to utilize the syngas at much higher utilizations than was initially believed in direct flame fuel cell research. So we found that. We then ultimately tested the fuel cell, and these are what are called polarization curves. Let me just explain a few things about them. One common question is, here at zero current density, so we're not drawing any current from the fuel cell, zero current density, the voltage is here, that's the open circuit voltage of the fuel cell. Why does it vary as the combustion equivalence ratio changes? Well, we can look at that theoretically. We're taking methane, we're oxidizing it at different equivalence ratios, and we're generating some composition of syngas and other products of combustion. We then realize that not all of those products of combustion are actually participating in the electrochemical reactions. It's only the syngas that's participating. So this is the fuel cell electrochemical reaction. This is what the fuel cell essentially sees. Now we can use thermodynamics, taking the first and second law and combining them together. We realize that the electrochemical work of the fuel cell is related to a change in enthalpy, entropy, and entropy generation. If we ignore the irreversibilities in this, and we're just concerned with what's the maximum, we can ignore entropy generation, and we can realize that the work is related to a change in Gibbs free energy. That Gibbs free energy, if we divide by the number of moles of electron per moles of fuel, and Faraday's constant, can be related to a voltage. So that's really basic fuel cells. That's how we determine what the voltage is coming from whatever fuel composition we have. Now in our case, we can find delta G because we know the composition of we can know the change in Gibbs free energy because we know the composition of the fuel. We also know that N in this case is going to be related to the dilution, right? It's not just, normally it's 2. We have 2 moles of electrons per mole of hydrogen, same for carbon monoxide. But in this case, we have very diluted fuel. There's only a little bit available. And so the reversible cell potential is related to a reversible cell potential for the syngas composition minus the effect of the dilution. And so this term right here basically says, well, we got to get rid of the fact that we have carbon dioxide and nitrogen that are diluting the fuel. That's an equilibrium constant. We can relate that to partial pressures. I can spare you with all the math. Ultimately, what we find is that once we go through those calculations, we can predict theoretically a voltage between about 0.93 and 0.98 volts. Well, If you take into account that there are actually some irreversible losses in the fuel cell, we find pretty good agreement within about 5%. So that's irreversibility at open circuit voltage. So you can actually predict some things about this system just using thermodynamics. Really exciting, right? But the good thing is, so now let's talk about what happens when we start to draw current. As we start to draw current, so we're increasing the current density, notice what happens as we increase the equivalence ratio. Initially, we kind of see essentially a curved line. This curved line, when it curves down like this in a fuel cell, that means that the fuel cell's not getting enough fuel. There's not enough fuel there available for it to actually go through the electrochemical conversion process it wants to go to. But as we increase the equivalence ratio, there's more syngas available, and it starts to become quite linear. You notice that? And that linearity is associated with the ohmic losses of the fuel cell, and so that's just the price of doing business, right? You got moving electrons through any kind of wire, you're going to have losses associated with that. So that's a good ohmic loss. We see that as the equivalence ratio gets high enough, we actually pretty much eliminate most of those mass transport losses because we have a diluted fuel, and we can have a fairly high power density, about 160 milliwatts per square centimeter, at least in this initial test. Okay. So now the next question, one more kind of theoretical question here for this early project. How does this combustion exhaust compare to what we'd like to have? We'd like to have pure hydrogen. Can you compare it to a pure hydrogen stream? And so we did that. Notice that the hydrogen and carbon monoxide both generate 2 moles of electrons per mole of fuel. Well, that means if this is our initial composition of exhaust, if you add the hydrogen and carbon monoxide composition together, you can create an equivalent pure hydrogen stream that has the exact same number of electrons available per unit time. And so what we did is we supplied this pure hydrogen stream and compared it to our fuel cell at these flow rates and compared it with our combustion exhaust stream. What you find is that the equivalent hydrogen potential, essentially, of an equivalence ratio of 1.2, 1.3, and 1.4 is, of course, significantly higher than the combustion exhaust. But what we found, surprisingly, is even though you only have less than 20% syngas within the combustion exhaust, you can actually generate about 33% of the hydrogen baseline. So it's actually possible to generate more power than you would expect from this diluted fuel. So actually, having a diluted combustion exhaust isn't as big of a disadvantage as you might otherwise expect it would be when you compare to pure hydrogen. So these are kind of the early developments. This is all the AMTech project. We got that done and we said, all right, well, let's make a system now. We kind of know this is going to work. We have some initial results that show that this could work. Let's develop an entire system. We did that through what's called an RQL combustor that's been integrated with a fuel cell. And I actually have a prototype of it here. You're welcome to pass that around so you can kind of get a sense of the dimensions. This is actually full scale of what it is in the lab. And so what we're doing here is we're supplying, again, fuel and air to our burner. We're going to a fuel-rich combustion, generating syngas, sending the syngas through the fuel cell, supplying a secondary air stream, which supplies air to the cathode, and ultimately will combust any of the remaining fuel. This is just a nice CAD schematic of it. And here's what it actually looks like in the lab. From the outside, we can't see the inside. That's why it's nice to have the prototype. RQL combustors, this idea of having a rich burn followed by a lean burn, that's a pretty common combustion technology, actually. It's used in the aerospace industry and jet engines all the time. We're kind of changing it. Instead of just burning rich and then burning lean just to reduce NOx emissions, we're trying to kind of take advantage of that situation and put a fuel cell in between. So that first test we wanted to run, we got this system built. What's the main concern? Well, I already told you that fuel cells don't thermal cycle. And that's kind of a major challenge. If you're going to put a fuel cell in a furnace, like we talked about in the beginning, and they don't cycle, there's not a lot of opportunities. So we didn't want to cycle 100 times or 200 times. We tried to cycle 3,000 times. Okay? And we cycled 3,000 times at a heating rate of almost 1,000 degrees Celsius per minute and a cooling rate of 350 degrees Celsius per minute. These kind of give you a sense of of the heating rate and the cooling rate. So these are the fuel cell temperatures right here. And over those 3,000 cycles, we saw about 2 millivolts per 100 cycle degradation. Compare that to about 0.35 volts per 100 cycles, which has been done in other tests on that. It's actually very, very low degradation. And we found that we had no degradation in power density, surprisingly, over those 3,000 cycles. So we haven't completely eliminated the seals. We used a microtubular solid oxide fuel cell, which has reduced sealing constraints. We were able to use that in this setup to achieve very high heating rates and thousands of thermal cycles. So 3,000 thermal cycles, to give you a ballpark, that would be roughly equivalent to a heating season. If you have an old furnace, some newer furnaces could be much less potentially. Kind of depends on the thermal mass in your building. So that was an initial test. You may think 3,000 cycles, you still got a long way to go to get to 10, 20 years, right? But huge progress compared to 100 cycles. Never, and to our knowledge, never has been done before. What we looked at then is we wanted to say, well, what did the anode look like before we thermal cycled, and what did it look like after? Notice that the anode surface has some large scale porosity here, and then you see some smaller scale porosity. Those are those black spots. After the thermal cycling, the large scale porosity is still very present, although we do see some small carbon deposits, but in general, very, very little carbon deposition after 3,000 cycles. This is about a 150-hour test that we ran consistently. And we do find that the carbon is much more present. So now we're looking at the cross section of the anode. The carbon is much more present near the surface, and in the middle of the anode, you see very, very little carbon. So carbon deposition, surprisingly, was not a major concern, and it shouldn't be, since we're not using large hydrocarbons here. We're converting it to carbon monoxide, and we're operating at the right temperature that this inverse boudoir reaction isn't a major concern. Now, we're getting back to the big stuff, right? Efficiency. So we can cycle, we can heat up rapidly. Can we get higher efficiency? Well, after 14 years of research, we broke 0.5%. And we were pretty happy about that, actually. It took some time, a lot of development with this system, but we broke 0.5%. It had never been done before. And so that was really exciting. But one thing to keep in mind here, one of the reasons why we switched to the microtubular solid oxide fuel cell is because it has large active area. We want to increase the surface area. We want to increase the ability to produce power. Once we increase the surface area of the fuel cell, we were able to break 1.2%. Okay. So still a ways to go, but we're approaching that point where we can actually convert enough of the fuel's chemical energy to electrical energy. Remember, I said we need about 1 to 2%. If we can convert that much, we could actually sustain the furnace potentially. One thing that's of interest here, from more of a just kind of understanding the chemistry that's going on. The fuel cell, you say to yourself, well, 1.2%, isn't a fuel cell more efficient than that? Well, remember, that's the system efficiency, right? When we actually look at the fuel cell efficiency is right around 25% for our particular fuel cells. If we got some ones that were made in industry, could be a little bit higher. But what's of interest here is that even though we're generating syngas, it's really the hydrogen that's driving this. About 87% of that efficiency is coming from the hydrogen being converted, and only about 13% from the carbon monoxide. Carbon monoxide reactions, that reaction I showed you, that half reaction, is much slower than hydrogen reactions. And so actually generating more hydrogen is of interest for us. Yep. So back to the big picture. This is where we started. We made some progress. We can get to 1.2%, we know. And actually, I think if we had made bigger fuel cells, we were kind of pushing our limits of how big we could make them in the lab. But I think we could get it a lot higher if we could make bigger fuel cells. What does that mean? Well, let's look now. Here's your furnace. Here's the blower we talked about. This is kind of the covering this, so you only see out here. But inside, there's a gas line. This delivers the natural gas to what's called an in-shot burner. This is essentially a venturi. It creates low static pressure here, which sucks air in, and then ultimately it mixes it, and it fires into this heat exchanger. You then blow air over the heat exchanger, and that's how you're getting heat for your house. So that's the basic picture. There's the problem. It's the blower, right? That's what consumes the electricity. That's why it's not resilient. Now, if we change it up just a little bit, we put a fuel cell stack in between the burner and the heat exchanger, and we essentially make a two-stage combustion with fuel cell power. Now we can actually provide that power directly to the blower so that this furnace not only provides heat, but it actually provides its own electricity too. Why is that different than a typical fuel cell? Well, again, typical fuel cell, fairly complicated. We're not steam reforming. And we actually, because of that, we don't need all these heat exchangers. And so it turns out our system becomes significantly simpler. We're just going to allow the combustion process to do all the reforming and the thermal management of the fuel cell, essentially. Much, much simpler. It actually saves us. You might think fuel cells are high cost. Well, fuel cells are high cost, but about 40 to 50% of the cost is actually associated with the rest of the system. So if we can simplify the system, we can significantly reduce the cost of this. And this is actually a reality, surprisingly. We went all the way, so we moved through that second NYSERDA contract. We moved on to the Nexus New York grant, and that allowed us to develop a full-scale prototype. So here's an actual heat exchanger that I gutted out of a furnace. And you can see here, this is how we're basically preheating our secondary airstream here. So we're having fuel-rich combustion that's happening in this portion of the heat exchanger. This little plate holds our fuel cells. We're then taking the secondary oxygen stream or airstream, and we're supplying it to the cathode. And then we're having a fuel-lean combustion into the downstream of the heat exchanger. And ultimately, this is what it looks like. Well, actually not the final picture, but one picture of it set up here in the Center of Excellence on the 4th floor. And we got power, which is good. We've still got a long way to go. So we got 150 milliwatts per square centimeter in this case. So it's not that 300 milliwatts per square centimeter quite yet. It took us a while to get there, but the system could actually work. That's at least what this initial test has shown us. There's a lot more to come. Does it have to be a furnace? Could it be anything else? Well, you could imagine it could be a hot water heater, right? Same general idea, hot water heater, burner, heat exchanger, water, same general technology. Hot water heaters run year round, so there's some advantages there. Could be a boiler. We could think of a very similar technology for a boiler. We could even think, because there's so much waste heat, if we use some sort of an absorption chiller, we could actually generate cooling as well. So we could have some sort of a tri-generation of cooling, heat, and power. We could even get a little bit more inventive. We could think about taking, for example, a diesel engine. What if we ran a diesel engine fuel-rich instead of fuel-lean? We generated syngas. The diesel engine generates power. We send the syngas to the fuel cell as a first stage cleanup, essentially, generate power, and then we take the remaining thermal energy with an organic Rankine cycle and generate more power, kind of a 3-stage power generation system. It's possible. We could even think about a gas turbine. This is a picture of a micro turbine. And again, changing the burner around a little bit, we can have a secondary power generation source within the gas turbine itself. So lots of different applications. But it begs the question, if you're still only getting 1% efficiency, what's the point, right? So is it possible, theoretically, to get higher than 1%? That was a question that started to kind of bother me about this a little bit before this time last year. I started to wonder, is it possible, theoretically, to push this? So this is our syngas composition. This is using chemical equilibrium, and you'll notice that chemical equilibrium results are fairly similar to the results we were achieving in the lab. So this is carbon monoxide generating from methane combustion. This is carbon monoxide from propane combustion and from butane combustion. And then here's the hydrogen for methane, propane, and butane. Is it possible to push this? Well, theoretically, one way we could examine this is to try and develop some sort of a Carnot limit. Probably a lot of you are familiar with the Carnot cycle, this idea that there's a maximum level of efficiency that a heat engine can achieve. What's the maximum level of efficiency that this system could achieve? Well, if we relate the voltage, this is a typical way of defining a fuel cell efficiency as a voltage over a thermal neutral voltage. The maximum the voltage could ever be is the voltage I've already derived. It's that reversible cell potential. That just relates to the composition of the syngas that's actually available. The thermal neutral voltage is related to the amount of chemical energy actually available. So that's related to a higher heating value through this reaction, complete reaction of the fuel. If we then compute that, and this is what it looks like simplified, okay? It's related to a change in Gibbs free energy over a change in enthalpy, and then those moles of fuel per mole of electron, or moles of electrons per mole of fuel available. We compute that for these 3 different fuels, and we arrive at a theoretical limit. So if you ever come across someone doing research in this area and they say the equivalence ratio of 1.1, I achieved an efficiency of 20%, you could be assured that something might be off, right? Because it turns out that it really depends upon the exhaust composition. As the syngas increases, we have more fuel available to electrochemically convert. And so in an equivalence ratio of 1.4, theoretically, we could start to get in the 5 to 10% electrical efficiency range. And if we can push this even further, we can start to see much, much higher electrical efficiencies could be possible. So maybe a lot more opportunity. So again, it starts to beg the question, well, you can't go past 1.4, you told us. So that's the upper flammability limit of methane. Is there a way that we can push beyond that limit? And that's where the idea of microcombustion came about. So conventional burner, these are the burners that, conventional size used in your furnace, your boiler. They have what's called this rich limit. And I've already talked a little bit about that. That was like 1.4 in our particular setup. They also have a lean limit. You can't get too lean either, otherwise the flame will extinguish. Well, there's something called super adiabatic combustion or super adiabatic burners. And by recirculating the heat and using it to preheat the fuel and air, you can actually have enough thermal energy there to sustain the reactions well beyond the upper flammability limit. So that was what, that's the idea at least. And it turns out that, this is one example of a researcher, and this is Schogel's group, who pushed the equivalence ratio well past 2. And as you can see, hydrogen concentration now significantly higher than what we achieved, as well as the carbon monoxide concentration. So if we can somehow push beyond that limit, maybe we can see a lot higher efficiency. To do that, we use a simple setup. This is actually from Maruta's group. This is a setup that they developed. And this is an experimental setup. Again, this isn't a full self-sustained system. But essentially, they take a quartz tube, less than 2 millimeter internal diameter. They're preheating the fuel and air with an external heat supply. This kind of mimics the idea of recirculating the heat to preheat the fuel and air. And you notice that the temperature of the incoming fuel and air increase. You can kind of stabilize it at a certain point, depending on what kind of combustion characteristics you have here. By doing that, we were actually able at so we stabilized our maximum temperature at on this wall at 900 degrees Celsius. And now we can sustain a flame even in an equivalence ratio of 5. Okay. So no longer 1.4, we can push well beyond that initial equivalence ratio. Well, what does that mean for our efficiency? What does that mean for syngas? Well, what it means is that ultimately we can take this fuel cell, combine it with this simple setup, this quartz tube, for example, which is our microcombustor. In our case, we did those. This is an experiment right here is just the quartz tube by itself. We're just examining the syngas composition and the flame. So that's what those pictures are. In this case, we combine it with the fuel cell. Again, not a self-sustained system, but giving us initial result. We used propane in this case. Methane has some reactivity issues. Methane is, because of the way the molecule is, it's very hard to break a CH bond and break methane down. So you actually have to get well beyond 900 degrees, and there's some sooting issues there that I won't get into too much, but happy to answer any questions on that. So for this initial study, we used propane as an example. And finally, at 800 degrees Celsius, we looked at, in this particular case, over 20% electrical efficiency. We were able to convert over 20% of the chemical energy into electrical energy in this setup. But we had to get fairly high equivalence ratios to do it. So there's opportunities here, right? Microcombustion is combining it with this simple setup and being able to push beyond that upper flammability limit. We might be able to start to approach electrical efficiencies that are very reasonable and could have some real opportunities in many of these other applications. So with that, we're almost done. We're getting there. One quick thing here, I just wanted to note, these reactions are kind of interesting if you haven't studied them out. So equivalence ratio of 1, again, we should have pretty much complete utilization of the fuel. We're trying to now talk about really high equivalence ratios. So at 750 degrees, this is kind of interesting. You see that the oxygen concentration, even at equivalence ratio of 1, is still 16%, very high. And it took very high equivalence ratios to start to utilize that oxygen. Well, as a result, these reactions aren't progressing very well. Your carbon monoxide concentration was fairly low, actually. This is worse than our initial results, right? Let's go back to the old way. Hydrogen concentration was even lower, but you notice that a lot of it, this process of converting propane down to syngas goes through this process. And it's kind of interesting here. You can kind of see it. So we have fairly high ethane, acetylene, and ethylene, right? These C2s. Methane breaks down first into the C2s. Those C2s then progress into methane and ultimately hydrogen, carbon monoxide, and then they go back to carbon dioxide and water as they're oxidized. So at 750 degrees, result syngas isn't actually that good. But at 900 degrees, we see a real change. These reactions that we're talking about are highly temperature dependent. And so as we start to increase the temperature, we start to see carbon dioxide is really significant concentration, at least at stoichiometry. We see much higher carbon monoxide concentration, hydrogen concentration, and ultimately kind of a change here. You notice that we have a lot of ethane, acetylene, and ethylene, but we see a reduction in those, and we see an increase in the methane. And so you kind of see that breakdown process happening as the propane converts down the line to first smaller hydrocarbons and ultimately to syngas. So that was the initial result. Since then, I don't think I have the results here, but if we control the flow rate properly, so now we're also controlling the temperature of the flame by controlling the flow rate, we are actually able to generate about 20% hydrogen. So about double what we initially started with. So just some interesting observations from microcombustion, and that's kind of where I'm going to leave you hanging. I think there's a lot more opportunity to continue to look into this. We've looked first at a conventional burner. We've found that we can combine it. We can run it rich. We then can combine it with a fuel cell. This 1% fuel utilization limit is no limit at all. We can push well beyond that. We found that we can cycle significantly by combining some of the merits of this setup, having the flame provide our thermal energy, bring it up to temperature rapidly, while using a microtubular solid oxide fuel cell to have high thermal cycling ability. We had no degradation during that thermal cycling test. We found that we can push that electrical efficiency at least beyond 1.2%, but theoretically I've shown that there's not a limit. We can go a lot higher. We maybe need to start talking to industry to really optimize this system going forward, but there's some potential here, and I see microcombustion as another area that kind of shows potential for this specific technology in generating large amounts of syngas, and then potentially creating a new kind of furnace, a furnace that doesn't require electricity anymore, but a furnace that is resilient, providing its own electricity and heat for your home. Thank you.
So thanks. I guess in the room, do we have any questions for Ryan?
So when you increase your efficiency to 23% compared to 1% previously, does that mean a 23-fold increase in electrical density output?
Yep. So that electrical efficiency is simply measuring the amount of electricity you're getting out compared to the chemical. So yeah, we can talk about a much smaller fuel cell, right? So if you want 500 watts and you're only at 1% electrical efficiency, you're going to need many more fuel cells. But if you can get that 23% efficiency, we need much less fuel cells. The system becomes a lot cheaper and potentially more competitive.
How do you compare the efficiency of the electrical generation to the local power plant?
Sure.
Efficiency?
Sure. So that is one area to think about. So power plant, typically you can see 30 to 40%, maybe even 50 if it's one of these nice new gas turbine power plants by GE. But of course, you're going to lose several percent of efficiency across the across the lines. So one of the advantages here is that if you're producing it in your home, you don't have to transfer the electricity all the way to where you need it. If you're producing it in your home, there's some advantages. Now, the real competition here, of course, is, if we're talking about this, kind of compared to what's already out there, we're talking about standby generators. We're talking about micro turbines or Stirling engines. Those are some of the other competing technologies that are kind of trying to work in this home heating and power generation. And a lot of those are hitting around 20% electrical efficiency. So if you really want to be competitive, we probably need to push that, but we need to get, higher to that 20-30% efficiency. One thing I would say though, that's kind of unique about what we're doing, a lot of the technologies that are currently approaching this, they're trying to take a furnace and then they're trying to take this other power generation system. They're two separate systems and you put them both at your house, right? Our system is kind of trying to essentially streamline the two of them together. So instead of producing electricity for your house at 20% efficiency and then maybe not having a use for the thermal energy, we kind of put the two together and now the cogeneration efficiency can be, 90%. So hopefully that answers your question. Yeah, I think there's definitely some needs for improvement if this technology is really going to become very competitive.
I was thinking, you already hit on it in your slide, you could use it on air handlers.
Yep.
And some air handlers use desiccant regenerators for dehumidification control. Yep. You need a source of heat to drive that. And one of the biggest consumers of energy on air handlers is fan energy. Yep. So you help defray some of the fan energy. You could get an energy benefit on two fronts. Desiccant dehumidification and an electrical benefit.
That's a great idea. That's something we'll have to explore.
Have you looked at any mixture of gases like propane, methane, pentane, different types of?
So, I mean, I've studied pure methane, ethane, propane, and butane up until this point. I didn't actually show you all those other ones. So we have used higher hydrocarbons. You can use butane directly and generate a lot of syngas. But one of the areas we're starting to look at is combinations. One of the challenges in microcombustion is that, as I mentioned, methane is very hard to reform. You need very high temperatures to do it. But natural gas actually isn't, because in natural gas, there's other hydrocarbons like ethane that allow it to be much more reactive. And so that's actually one of the areas we're starting to explore is direct natural gas could have some real advantages in the microcombustion setup.
So I saw you like this chamber is always a uniform cylinder. So is there like a reason like why you always choose uniform geometry? So this chemical reaction is kind of propagation of some information that you have starting point and ending point. So do you think if you optimize the shape, like
Sure.
have this
Sure.
non-uniform?
Yeah, let me go back and just show one thing here as I answer that.
For the people on the webinar, if you could summarize the question.
Sure. So I think the question is, as I understand it, is that you have a very uniform tubular shape. Could you optimize the shape? Could you use a different shape to try and improve the performance of the cell? That's how I understand the question. So let me just jump back here a minute and just say one thing that's really maybe key for answering that question in case anyone missed this. So when it comes to a fuel cell, it's all about the area, right? The amount of area that the hydrogen and the oxygen have to meet up at the boundary dictates how much electricity you can actually generate. And so you're right, if this is a straight boundary, there's only so many sites available. If this boundary is extremely jagged, we can potentially have a lot more sites where this electrochemical reaction can take place. So why did we use the straight ones? Well, that's the manufacturing equipment that we have available. Generally, extrusion machines make very nice uniform shapes. But is there an opportunity there? I think there is. And that's actually one area I'm really actually interested in exploring going forward, because ultimately we've been able to utilize a few percent now with the syngas. Well, if we're really going to show that this can work, we're going to need to utilize 30, 40, 50%. And one key to doing that is improving that boundary by increasing that area significantly. So it's a great question and it's a great direction. I think that's where we need to head.
And I saw you have so you make a real device, the larger multiple like this channel, and so at there's a bending part, you have some like wrinkle, non-uniform.
Are you talking about the furnace, some of the non-uniformity in the furnace heat exchanger?
Yeah, that's due to manufacturing, or it's like you intentionally introduce at the transition product. Yeah.
So I think the question is essentially why is there crinkling in the heat exchanger? So we didn't make this. This is a real furnace that I actually gutted out and took it from. We actually went to the manufacturing facilities of one of these, and it's interesting. How does this form? Well, they have a piece of steel. It's in a nice, it's a pipe essentially. If you were to just bend it, it would just crinkle. It would just break essentially right at the midpoint. It's not going to make this nice uniform bend. So they have these nice machines. And what the machines do is they introduce these little buckle points, essentially, that allow it to form into kind of this curved shape very uniformly.
So that the initial is uniform. During the manufacturing process, they intentionally introduce this one.
In order to get it to bend and kind of make a complete 180 degrees. Yep, that's an intentional. Yep. Great question.
Yeah, I have one last question. And many times we try to seek inspiration from nature. Like for the fuel cell, is there like a similar, our nature or biology has similar structure that some animal or some plant, they use this fuel cell as energy resource that if possibly can find some structure and to get some inspiration or if not.
So the question, as I understand it, is our fuel cells kind of inspired by some sort of a natural process? Is that kind of what?
It kind of reverse. So, yeah, kind of.
Yeah.
So in the nature, so that like some animal plant they use fuel cell like mechanism to generate this energy
Okay.
motion.
Okay. So I know that there are researchers who are studying, I think there's certain kinds of algae that can generate hydrogen actually. And so there's some work being done there. You know, can we go through, have some sort of a natural source actually generate the hydrogen for us, and then it's kind of free and it's much more, sustainable in that. There's also biofuel is another area. And one alternative project that we've looked at is, we have wastewater treatment facilities. Well, when you have this wastewater treatment facility, they generate a lot of methane that we can utilize. It's not a natural source necessarily, but you're bringing the methane out of the wastewater treatment facility. Sometimes it's utilized efficiently, sometimes it's not. Sometimes you can see over here in Syracuse, they flare up the excess biofuel that's available, and so it's actually not being utilized very well. But that's sort of a natural source. We're kind of recycling waste, and there's some opportunities possibly to work in that. But I know there are researchers who are looking at different kinds of species that can generate hydrogen. I'm not as familiar with it, so I don't want to speak from an expert point of view. But
Yeah, I just had a question. So I didn't catch, why is it called micro-combustion? Really, you're just preheating the fuel in there towards it with micro-combustion?
Generally, so the reason why that came about, let me just, actually, I think I can skip ahead a little bit here. So in a conventional burner, there's something, so we talked about the upper flammability limit. There's also an extinction limit that's associated with size, okay? So a typical flame arrestor, you might be familiar with flame arresters. What are they? They're just really small diameter ports that the gas has to pass through. Because the wall is so close to the flame, it basically sucks the thermal energy out of the flame and extinguishes it. And so actually at a diameter of 2 millimeters, most flames will not propagate. They'll actually extinguish. It's not possible to propagate a flame under normal conditions at this small of a diameter because the wall will just take the thermal energy and it'll extinguish the flame. And so microcombustion came about when they said, well, can we operate below that limit? And using heat recirculation, you can. So that's kind of where the term came about, and it's mostly because they call it micro, even though it's really milli, right, millimeter. But that's where it came about. Great question.
Any other questions? Thank you, and thank Ryan. I'm going to add one little postscript to Ryan's introduction. So Hugh pointed out, Ryan earned all 3 degrees at Syracuse University in Mechanical and Aerospace Engineering. So Ryan came to Syracuse University as an undergraduate student in industrial design. And I've been here a long time. I think this is the first student I've ever met that started in industrial engineering or industrial design and got a bachelor's degree in engineering and then actually went on to a Ph.D. So Ryan has a gift of communication, and I think that part of that gift is rooted in his skills in industrial design. I think he's going to be a spectacular professor at Arizona State. We're sorry to see you leave New York State, but we wish you the best in Arizona. And I'm going to invite everyone here to join me in thanking Ryan today and wishing him the best, and then join us for refreshments afterwards.
Thank you.